Let's study ICSE 10 Standard Physics Chapter 10 Electromagnetism. Electromagnetism. Electricity and magnetism are the two faces of the same coin. Wherever there is electricity, there will be a magnetic field. And wherever there is a magnetic field, electricity can be induced. This was discovered by Hans Oersted in this experiment. Here, when electricity passes through this circuit, we notice that the magnetic needle is deflected because of this electricity. Ideally, the magnetic needle should point in the north-south direction, affected only by the Earth's magnetic field. But as soon as you switch on the key, it is deflected like this, meaning that this electricity is producing its own magnetic field, which interferes with the Earth's magnetic field, and the resultant magnetic force acts on the magnetic needle. And he repeated this experiment with different configurations. For example, here you can see he has switched the direction of current, then the deflection also changes. And this happens everywhere around the wire, above it, below it, to its left or right, it doesn't matter. That means there is a three-dimensional magnetic field which is invisible to us, which is creating this effect. So here, this detail of the experiment is cancelled. Observations have to be read, and then the explanation is simply that it has its own magnetic field. Inference, which is conclusion: a current or moving charge produces a magnetic field around it, and this is called the magnetic effect of current. That's the definition. Next, section 10.2, the first paragraph and the details of the experiment are cancelled. We have to understand the experiment only with the help of the diagram. We won't be asked to explain the experiment, rather we'll be asked questions based on the experiment. So we have to understand the experiment first. Imagine that there's a long rod, a wire rather, of copper or any other metal would do, and electricity is passed through it. We can't see the magnetic field directly, so let's pierce it through a cardboard and sprinkle iron filings on it and gently tap it. You would notice that the iron filings create concentric circles around it. This helps us to see the magnetic field around this current carrying conductor. But we can't know the direction of the magnetic field. So let's redo this experiment with the help of magnetic needles. We'll keep the magnetic needle at various points, and wherever the North Pole points, we'll point out there. And then after having multiple points on the cardboard, we will join them with a pen, and now we will see again the concentric circles being formed. Not only that, we see that the direction is clockwise in this magnetic field. And notice the direction of the current, it's downwards. This means that when the direction of current is downwards, the magnetic field is clockwise, as you can see. So if the direction of the thumb is the direction of the current, then the direction of the curled fingers gives us the magnetic field. So if the current was upwards in that same diagram, then the magnetic field would be in which direction? It would be anti-clockwise. And this is called the right hand thumb rule. It helps us to identify the direction of magnetic field lines if we know the direction of current in a current carrying conductor. It's a straight conductor, by the way. Now, there are some observations which we need to learn. So give the heading observations here. First of all, the concentric circles are perpendicular to the wire. So if the wire is vertical, the cardboard is horizontal and the wire pierces the cardboard. So imagine this in 3D. Second, if we change the direction of current, then again we'll get concentric circles, but using a magnetic needle, we would notice that the direction of the magnetic field would be opposite. That is, it will be anti-clockwise. And if we increase the amount of current flowing through it, that's why we have a rheostat. You can change the amount of current flowing through the wire. It's a variable resistance. We would notice that more the current, stronger is the magnetic field, so denser will be the concentric circles. They will be close to each other. And weaker magnetic field means they'll be far away from each other, means it's weaker. So these were the observations. Note that the magnetic field that we are discovering is not entirely because of the electricity, but it is getting influenced by the Earth's magnetic field as well, but that's very minor component. However, there might be some points around the electric current where there is no magnetic field, and they are called neutral points. Incidentally, at such points, the Earth's magnetic field and the conductor's magnetic field are equal and opposite and cancel each other. You've studied this in 9th standard. They are called neutral points. So let's read the statement of the right hand thumb rule. It's also called corkscrew rule. If we hold the current carrying conductor in our right hand such that the thumb points in the direction of flow of current, then the fingers encircle the wire in the direction of the magnetic field lines. Also notice that the magnetic field of the Earth in a limited space is uniform. That you will study in 9th standard, that Earth's magnetic field lines are parallel to each other and equidistant in a small area. So they are called uniform. Not very important from this chapter's point of view, just good to know information. Now section 10.4. We studied about magnetic field around a straight conductor. But what if we take a loop of wire and current flows through it? Then what happens? The experiment's details are not important. We just have to know the observations and the conclusions here. So imagine this part of the loop, okay, P point. Ignore this part. This is like a conductor. Here the current is going upwards. So use your right hand thumb rule and see how the magnetic field should be. It should be anti-clockwise. That's what we'll draw on this cardboard. On the other hand, at point Q, the current is going downwards. So how would the magnetic field look? Downwards. So it will be, so if it's downwards, it is going clockwise. Yes. Yeah, during the board exam, you can just figure it out with your hands, but be careful. The teacher should not think that you're trying to signal somebody something. Next, this paragraph and this paragraph is cancelled. Observations. We observe that here it's anti-clockwise and here it's clockwise, but both of them become parallel in the center. So it's like the fields are going inside through the loop, like this. So near P and near Q, the magnetic field is strongest. That is why the lines are so close to each other. And in the inner space, the direction of the magnetic field lines is same. This is also going inwards and this is also going inwards. So in this area, they can be considered as uniform magnetic field. They're almost parallel and equidistant to each other. To increase the strength of the magnetic field, we can do two things. Number one, increase the current through the loop. Second, have multiple loops. You see, each loop will have its own magnetic field, which will add up because they will be in the same direction. So more the number of loops, the stronger magnetic field we get. And many loops together is called a solenoid. And if we insert the central area with a soft iron bar, because right now it's filled with air, if you have a soft iron bar, then it's called an electromagnet, which will be quite powerful. Even this circle will have a north pole and a south pole. So remember, north pole always is the beginning point of magnetic field lines. So imagine this was the loop of copper wire. I said that the magnetic field lines are going inward like this. Like this it's going. So if it's coming out from here and it's entering from here, so this face is the south pole, whereas this face is the north pole. It's like a magnetic disc. This will be the south pole and this will be the north pole, because the field lines start from the north pole and go into the south pole. So from north pole to south pole. A trick to find out which one is north pole and south pole in a coil carrying conductor current is that if current is flowing anti-clockwise on this face facing you in the dark, then that face is the north pole. But if it is flowing clockwise, then that face is the south pole. So again, out here, what's happening is current is moving clockwise. So if current is moving clockwise, this face should be your south pole, and the other face, if you flip it, you would see the current would be flowing anti-clockwise here. So that would be called the north pole. So this clock rule really helps us to figure out. So cancel this, give the heading as observations, which I've explained, and the clock rule is there. Next, let's mark the definition of a solenoid. A solenoid are many such coils together, but make sure that the length of the solenoid should be greater than the diameter. So if you have this, say, 5 centimeters diameter, then the ring's combined length should be greater than 5 centimeters. It should not be a very short cylinder. It should be quite long. Only then we call it a solenoid. Experiment paragraph cancelled. Even this paragraph is cancelled, but we have to understand this experiment again. So this is the same as the previous one, but instead of one ring, we have multiple rings together. It's a continuous wire, which will act like an electromagnet. Each of the loop will have its own magnetic field, and they will all add up. Now we have to judge which one will be the north pole and which one will be the south pole. So notice here, okay, this face PP dash. So I can see the current is going up and then going down from behind, which we can't see. You can only see this arrow up. So mark that arrow, and even here mark an arrow up. That's the correct direction of current. Notice up, down, up, down, up, down, and finally down and back again. So if it's going up from front and behind, it's going down. So if I look at it from this angle, this is anti-clockwise. That means this face is a north pole. Now let's look at QQ dash face. Again, same thing. Current is going up from front and it's going down from behind, like this. So if I look at it from this side, this angle, it's clockwise. So this is the south pole. And then we draw the usual magnetic fields from north pole to south pole. It looks like a bar magnet, isn't it? So double tick this diagram. You have to label all the parts as well. Also double tick figure 10.2 and figure 10.4. They can ask you to draw this in exams. Now the observations, give the heading observations. We have a uniform magnetic field inside the solenoid. Can you see the lines are parallel to each other, almost equidistant to each other? So it's a uniform inside. On the outside, we see that the magnetic field lines are denser at the poles and far away near the center. Just like a bar magnet, it behaves like that. Third, the magnetic field will be increased if the number of turns are increased or the current is increased. And right now in the center we have air, and air has low magnetic permeability. But if we insert a soft iron bar which has a high magnetic permeability, or in very simple language I would say it is a good conductor of magnetic fields, then it becomes a powerful electromagnet. So mark that fourth point as a GR out here. What would happen if we switch the direction of current? Then the current will flow like this and down. In that case, this will become the north pole and this will become the south pole. So in exam they might give you a diagram and ask you to identify which is the north and south. So keep practicing with bangles. I've used silver bangles because silver, grey and purple represent wisdom. Y'all can use yellow and red bangles because it represents the passion in your heart. Next, similarities between a current carrying solenoid and a bar magnet. Mark the first point as a GR, just like the fourth point was a GR out here. This asterisk and all is irrelevant. You don't have to take those markings. Well, both behave similarly. If you hang this freely, even this will rest in the north-south direction because it will be under the influence of Earth's magnetic field. Even it will attract ion filings towards it. So it has both attractive property and directive property. But there are some dissimilarities. The strength of a bar magnet cannot be changed, but for electromagnet or solenoid, it can be changed. And even the direction of polarity, north pole, south pole, can be flipped. But in a permanent magnet, a bar magnet, it can't be flipped. That's why electromagnets are so much more useful than permanent magnets. First paragraph cancelled. Mark this as a definition. And then a repetition of 9th standard stuff. Cancel this first paragraph and this paragraph. Although the use we have to learn. This eye-shaped electromagnet is useful in relays. Double tick it. You should have all the parts, especially the arrows should be there. Be careful about the arrows. Notice that the current is always from positive terminal to negative terminal. And this, again, just practice this. Here, the current is going down from the front and going up from behind. So from this angle, it's clockwise, isn't it? This is clockwise. So we call it South Pole. And this will be the North Pole. Clock rule is the only way you can figure it out. There is no other trick. Even figure 10.8, double tick it, horseshoe electromagnet. Make sure that while drawing, the arrows on this P arm and arrows on the Q arm are opposite to each other. Then only it will work properly. Arrows matter. And you'll figure out that this is South Pole and North Pole if you use the clock rule. The theory part is all cancelled. Not important. Uses are there. It is used to make AC generator, DC motor, electric bells, etc. Now there is a note which you can cancel. By the way, it will be repeated later on. So if you don't cancel, it's okay, because we have to know that the source of AC frequency is of 50 Hertz. How to increase the strength of an electromagnet? That's easy. Increase the number of turns in the solenoid and increase the current flowing through it. Now, instead of soft iron, if we use a steel as the core of a solenoid, then the steel will behave like a magnet even when the current is switched off. That's because it has high retentivity, magnetic retentivity. So mark it as a GR and it becomes a permanent magnet. Which simply means it will remain a magnet for a very long time. But soft iron has low magnetic retentivity. Remember, high magnetic permeability but low magnetic retentivity. That means it does not retain its electromagnetism once the electricity is switched off. Permanent magnets are used in ammeter, voltmeter, galvanometer, etc. and in magnetic compass. The differences are very well known, and you can mark the last 4 points as advantages, in fact, which I mentioned. Here, magnetic field strength can be changed, very strong magnetism can be produced, polarity can be reversed, and it can be demagnetized. Whereas a permanent magnet, none of it is possible. Uses of electromagnet. Well, useful for lifting heavy iron loads. Second point is too small, cancel it. Useful for separating iron pieces from debris, that is waste. To remove pieces of iron from wounds. Iron Man used it. That's Tony Stark used it before he was Iron Man, because shrapnel from an explosion pierced his chest. And in scientific research, magnetic properties of a substance can be studied. It is also useful in devices like electric bell, telegraph, etc. Let's see how an electric bell works. These are the parts. Double tick figure 10.9. Theory is cancelled. Working has to be read. It doesn't have to be learned. You just have to understand how it works. So you're able to answer any question like, what is the function of this or that? So notice here that electricity passes through this wire, this circuit. You can draw a simplified diagram as well. Something like this, but not the blue part, of course. So when you switch on the current, electricity flows through it, circuit is complete. This becomes an electromagnet. Note, arrows are opposite, that's important. Then this armature will be attracted towards it, and when it is attracted, then the blue shape comes into the picture and the hammer hits the gong. But when that happens, it is no longer in contact with this contact screw. That means the circuit is broken. Electricity won't flow. That means it will no longer act like an electromagnet. It will no longer attract this armature, metallic strip. So, like a spring-like action, it will go back to its original position. But when that happens, it once again comes in contact with this adjustment screw. The circuit is completed, electricity flows, this becomes magnetized, and the cycle repeats itself. Magnetism, magnetized, demagnetized, magnetized, demagnetized. Circuit is broken and closed, broken and closed. This keeps on happening, and the hammer keeps hitting the gong, and that's how an electromagnet bell works. So make sure you read the theory, the working part, and keep looking at the diagram for that. Note, even if I don't use a battery and I use a AC source of current, alternating current, the direction of current will keep changing 50 times per second. So the North Pole and the South Pole will keep flipping, but that doesn't affect the working of the bell, because no matter which is the North Pole or the South Pole, this armature will be attracted to the electromagnet, so it will work equally well. But which is the North Pole and South Pole in this diagram? Use the clock rule and find out. That is an assignment for you. The solved examples of this chapter, particularly this chapter, are the most important because they are application based, and this is a kind of chapter where one worries about what kind of question can possibly be asked. They can ask you the working of electric bell. Well, the solved examples, which have no numericals by the way, are the perfect way in which you should study. Answers are also given, you should study them well whenever I give that assignment. And most of the questions in your exam will be from exercise and essays. I would say if you study the exercise and essays, 90% of this chapter is done. It covers almost all important questions which are possibly going to come in the board exam. So exercise also has to be studied well whenever I give you this homework. Some answers are given, some are not. No numericals, that's a good thing. Now the B part. First of all, force on a current carrying conductor in a magnetic field. Here you would notice that if I have this circuit hanging by threads and current is flowing through it, and if I bring a magnet near it, the conductor will move, will be attracted or repelled by this electromagnet. That makes sense because as electricity is flowing through the circuit, through this conductor, it will have its own magnetic field, and when there are two magnets nearby, definitely there will be attraction or repulsion. So this force which acts on a current carrying conductor, or rather on any charge which is moving in a magnetic field, is called Lorentz force. But this will work only if the current or the charge is moving in a direction other than the magnetic field. Which means that if the magnetic field is from left to right and the current is also moving from left to right parallel to it, it won't experience any force. Only if the current is moving at an angle to the magnetic field, any angle, then it will experience the Lorentz force, due to which it can move without even touching it. So the experiment theory is all cancelled. Directly come to the observations, which I've already explained. The fourth observation can be cancelled. The magnitude of the force is totally cancelled, including this equation. But just for your information, you should know the unit of magnetic field, which is called Tesla. Now, there is a story behind Tesla, which I'll explain in class. Another unit is Weber per meter square or Newton per ampere per meter. You need to know all of these units. But if they ask SI unit in exam, it is Tesla, the shortest one. But how would we know in which direction does it move? Well, that is given by Fleming's left-hand rule for the direction of the force. So the Fleming's left-hand rule states that if your thumb, your forefinger and your middle finger, central finger, are mutually perpendicular to each other, like this, left hand, and if the thumb represents the motion of the conductor, the forefinger represents the magnetic field, and the central finger represents the current. Come on, lift your left hand and your fingers outstretched and learn it right now. This will require a lot of training. How to remember it? Central finger current, forefinger field, magnetic field, and thumb will be the motion. Learn this word to word. This helps us to understand simple DC motor. How does a motor work? For example, in your fan, there is a motor. It rotates because of Fleming's left-hand rule. In our reduced syllabus, this is not there. Section 10.12 is entirely cancelled. But remember, which rule is applicable in DC motor? Fleming's left-hand rule. Now we move on to section C, first paragraph cancelled. Now notice that here we have a solenoid, but there is no battery or source of current, so no electricity should flow through it, right? It's just wire, that's it. But if I bring a magnet near it and move it, automatically current is induced in it. I'm not even touching it. The galvanometer proves that there is current. from where did the current get induced? Well, it's called electromagnetic induction. You see, this magnet has a magnetic field around it, which we can't see. This magnetic field around it will affect the solenoid and create electricity inside it. This is an amazing phenomenon. And notice that the direction of the current depends on a few factors. For example, when you bring the North Pole nearer, then current is flowing like this. When you're pulling it away from it, then the direction of current changes. Or if you flip it to the South Pole and bring it near it, then also the direction of current is opposite to this original direction, which was here. So how will we know in which direction will current flow? Well, there are two rules to help us decide this. But before that, let's understand the concept of magnetic flux. Mark this as a definition. So imagine just one coil. There is a magnet here. The magnet has its own magnetic field, which you can't see. Some of the magnetic field will pass through this as well. Okay, so this is a coil, and this is your magnet. And as I move it in and out of it, the magnetic field of this magnet will also move in and out of it, but I can't see the magnetic field. Now, as it is far away from the coil, let's say only 3 magnetic fields were passing through it, because the farther away you are from a magnet, the weaker is the magnetic force, so less lines will pass through it. But as you bring it closer, denser and denser magnetic field will now pass through the coil. So the number of magnetic lines per area, or let's call it magnetic flux, linked to the coil is changing. And that is why electricity is produced, because of the change of magnetic flux through a coil. So when I am moving a magnet or I'm moving the coil, it doesn't matter. What matters is the number of magnetic field lines passing through this coil is changing, or the magnetic flux is changing, and that will induce electricity. So your mechanical energy of moving it is getting converted into electrical energy. It's not magic. It is still obeying the law of conservation of energy. And that's how all generators work. Your thermal power plants, your nuclear power plants, the dynamo. Electricity is produced because of this phenomenon of electromagnetic induction. Now tell me, if both of them were moving with the same speed, then would electricity be induced? Why? Why do you think so? Because there is no change in magnetic flux. The same magnetic field will pass through the coil. Still, there has to be a relative motion between them. And the faster the motion, the faster the change of magnetic flux, the higher the rate of change of magnetic flux, more is the current produced. Another way of producing a lot of current is increase the number of coils. And one more way is use a very strong magnet. One more, okay, increase the area, surface area, or rather the cross-section area, not surface area, cross-section area of the coil. So these are the factors affecting the amount of current in the coil. All of these points should be learned, but the experiments have to be just read. Conclusion has to be learned. And this explanation was beautifully given by Faraday, one of the geniuses of physics. Mark the definition of electromagnetic induction here. Note is cancelled. Section 10.14 is cancelled. Now, which face of this coil will become, in which direction will current flow? Will it flow clockwise or anti-clockwise? How to decide that? So there are two rules. One is Fleming's right hand rule and the other is Lenz's law. Let's start with right hand rule. Notice this is not the thumb rule, okay? It's just called Fleming's right hand rule. Don't be confused between the various rules. So if you have your thumb, forefinger and your central finger outstretched, mutually perpendicular to each other, come on, practice it with me. If the thumb represents the motion of the conductor and the forefinger represents a magnetic field direction, then your central finger will be the direction of current. So they are mutually perpendicular to each other. So again, how will you remember it? Thumb is motion always, forefinger is field, and central finger is current. Same as the earlier left hand rule. But remember, in the left hand rule, we provided the current and we obtained motion. But in the right hand rule, it's applicable when we are providing the motion and we are obtaining the current. So understand the difference between the two. The left hand rule was applicable for motors. The right hand rule is applicable for generators. Motor converts electrical energy to mechanical energy, but generator converts mechanical energy to electrical energy. Learn the rule word to word. But a more useful law is Lenz's law, which says that the direction of the induced EMF, that is induced current, is such that it opposes the cause which produces it. Wow. Let's understand this here. Here the north pole is getting pushed towards this face. Now, as per Lenz's law, it would like to resist it. It's stubborn. No matter what we do to it, it always wants the opposite. It would like to repel it. How can it repel it? By becoming a north pole. How can it become a north pole? If the current is anti-clockwise. Hence, the arrows of the current are like that. Now we understood how to find out the direction of current being produced. Because only if it is like this upwards, it goes back up and comes down here, arrow down, down, down. So this is anti-clockwise if you look at this face. So it goes up from behind and comes down from front. So that's anti-clockwise. So that's a north pole. Why does it want to be a north pole? So that it can repel it. But if I pull the magnet away from it, it would like to attract it. Because it's confused. When somebody comes close to him, he pushes them away. When somebody leaves him, he wants them to stay. This person has real relationship troubles with magnetic field, of course. So, when we are pulling the magnet away from it, it would like to be the south pole so that it can attract it. And how can it be the south pole? If the direction of current changes to this. That is clockwise now. When it was stationary for a fraction of a second, of course, no current flows. If we flip the north pole and south pole, again see, this will like to be the south pole to repel it. It doesn't want it to come near. But if I pull it away, it would have become the north pole. So you can see the direction of current changes, it becomes zero, changes, becomes zero. That's why it's called alternating current. And now we know why the direction keeps changing. 50 Hertz is the frequency in India for alternating current. If you draw the graph of the EMF being produced, it's somewhat like this, a sine wave is formed. Fortunately, section 10.15, that is AC generator, is entirely cancelled in our reduced syllabus. But remember, the Lenz's law is applicable for AC generator. And here, this paragraph is important. And there is a correction out here. It should be from A to B. Whatever I'm not cancelling is supposed to be studied. I am giving you a lot of cancellations, but whatever is not cancelled cannot be ignored. So now let's jump to section 10.16. Frequency is 50 Hertz. The polarity changes 100 times every second, even though the current's direction changes 50 times per second. Difference between AC and DC is cancelled, but we do have this difference between direct current and alternating current in a table format. So just 3 points. The first 2 points together is called a definition. Here the direction is fixed, here it is not fixed, it keeps changing. Not only the direction, but you could see even the magnitude keeps changing. Maximum current, zero current, maximum current, zero current. And zero current is for only a fraction of a second. Remember, when the motion stops for a fraction of a second. This can be obtained from a battery, this is from a generator. But what is the advantage of AC? It's cheaper to generate, it is more efficient than DC generator, and that's where Tesla was a genius. Because he supported AC generator, he invented AC generator, whereas Edison supported DC generator. It's very easy to convert AC to DC, by the way. And the magnitude of AC voltage can easily be increased or decreased. In our households, we get EMF of what, 220 volts or 240 volts in our households. But in the power station, it is produced at 11,000 volt. Then it is increased to 32,000 volt, because higher the voltage, less is the loss of energy while transporting it. Then it comes to the city where it is stepped down again to 33,000 volts, then reduced to 11,000 volts, and finally 220 volts in our houses. In industries, of course, it's higher, it's 11,000 volts or something. So we can increase and decrease voltage easily with AC using a transformer, which is not in our syllabus. DC, we can't increase and decrease it, and that would lead to a lot of wastage of energy while transmitting. That is why we use AC current in our households. Section 10.17 is not there in a reduced syllabus, and 10.18 is not there in a reduced syllabus, and with that the chapter is over. Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.